Hi everyone, my name is Shreya Mogolothu, and today we're going to be talking about finding the exact min cut of a graph in the streaming model. And I want to thank Northwestern for allowing me to present today. Okay, so what is our problem? So our input is going to be some graph on vertices and edges, and then our output is going to be the min cut of this graph. A cut of a graph is just specified by some partition of edges, partition of vertices. So for example, ABC on one side and DEF on the other side. And then the size of this cut will just be the number of edges that go across this partition. So in this case, the size of this cut is 1 because there's only one edge CD crossing the partition. And what we want to output then is the cut of this graph with the least size. So in this case, it is ABC on one side and DEF on the other side. And what we want to output is the partition of this cut, so what I just specified, and then also the size of this cut, so size of 1. Okay, and we're going to be doing this in the streaming model. So our input is still going to be some graph on vertices and edges, but what we will know are the vertices, and what we don't know in the beginning are the edges. And we're going to know the edges through a stream. So the edges are going to come to us one by one. So we get the edges through the stream, and throughout the algorithm, we have to maintain minimal storage. So the storage that we want to maintain is like O tilde n space. So that's like O of n times polylog n. So it could be O n times log of n or n times log of n, just n times some polynomial of log n. And at the end
Can I ask a question actually?
Yes.
So is the number of nodes known in advance, and is that valuable, or you don't care?
Yeah, so we know the vertices in advance.
Okay.
Okay. And at the end of all of this, we want to, again, just output the min cut of G.
I have another question.
Yeah.
So here, you don't have any source or sink, right? So a trivial partition where you put everything into one will give you a min cut, right? So
Okay, so so our min cut needs to have like a non-empty partition. So both partitions need to be non-empty.
that is only constraint?
This is also an unweighted, undirected graph. But yes.
Okay, fine.
I guess it's the same as finding like the edge connectivity of a graph.
Yeah, exactly.
Yeah.
Okay, sounds good. So one trivial way that we could solve this algorithm is just, as we're getting the stream, just store all the edges in the graph. And so now we have this like entire graph, and we can just run any min cut algorithm on it to find the min cut size and partition that we wanted. The only issue with this algorithm, though, is that we need at least n squared space because we're storing all the edges, which we can't have, right? Because our target was going to be O tilde n stored space. So some observations. So if we have any graph G, we know that the size of the min cut is at most n minus 1. And we know that because we can just make a trivial min cut by putting one vertex on one side and everything else on the other side. And then the size of this min cut will just be the degree of this vertex. And we know that the max degree is n minus 1. So the max size of any min cut will also be n minus 1. Okay, and a couple of definitions. So when I talk about a cut C, I might mean the partition of C, so A, B, C, and D, E, F in this case, or might mean the size of C, so 1. But you will know which one I mean from the context, so that will be clear. And then secondly, we're going to denote C star as the min cut of G. So then our goal is to output the partition and size of C star. Okay, so now we'll go over to some intuition and build up to the algorithm. So any one-pass algorithm that returns the min cut and size of the graph must take at least n squared edges. This is shown by Zucky. So we cannot have a one-pass algorithm that gives us our answer. So we look to a two-pass algorithm. So what we're going to do is not only get the input once, but we're also going to get the input a second time. And then after getting both sets of inputs, then at the end, we should be able to return the partition and size of our graph. Okay, so we want to know what exactly are we going to do in these two passes. So we see that we want to return two things, right? We want to return the partition of the min cut as well as the size. So we're going to delegate different tasks to these passes. So we're going to say in the first pass, what we're going to get is the partition, right? And in the second pass, we should be able to get the size of this partition, of this cut. Okay, so it'll look something like this. So in the beginning, in the first pass, all we want to do is get the partition of the graph. So it'll look something like this. So ABC on one side and DEF on the other side. And then in the rest of the algorithm, we're just going to get the size of this partition. So how exactly are we going to do this? Okay, so all we need to do is just take the partition, right? And as we're getting the stream, only store those edges that go across this min cut. So in this case, we're only storing edge CD because that's the only edge that crosses the cut. And at the end of this pass, we'll be able to get the size of the min cut, and then that fulfills all the criteria that we wanted to return, and so we're all good. Okay, so I want to say a couple of things about storing the edges across this partition. So we're taking a graph and only storing the edges that cross the min cut, right? So all other edges are kind of useless to us. They don't cross the cut. So what we can do is just say, OK, I'm going to subtract all useless edges. And this is basically like saying I'm only going to store a supernode graph. So the supernodes here are just consist of vertices that are on the same side of the min cut. So ABC is on the same side of the cut, and DEF is on the same side of the cut. So we're only storing the edges that go across the supernode graph. OK, so what have we said so far? We've said that in the first step, in the first pass, we're going to get the min cut partition, and in the second step, we're going to get the size, which is basically like storing the edges across two supernodes. So what we want to focus on then is how exactly we're going to get this min cut partition in the first step. OK, so remember, though, that we cannot store all of the edges and then find the min cut partition that way, because that will take at least n squared edges. So what we want to do is sparsify the graph. And all that means is we're going to construct a new graph from the stream, but with fewer edges. And note that the edges in this sparsified graph can be weighted, because if we're not storing some edges, we might want to increase the weights of some other edges so that the properties of this new graph are similar to the properties of the original graph. So for example, what we can say is if we start with this input graph G and we get the edges through a stream, we might end up with some sparsified graph H. And H has a lot of similar structure to G, except it is missing a few edges. So that's kind of what we're saying, because we cannot store all of the edges in the graph. But the thing is, we want some useful guarantees about the properties of H, right? We want H to preserve a lot of the information that was in G. And specifically in our case, we want to preserve important information about the cut sizes in H, because we're trying to find the minimum cut. So let's look at a couple of cut sizes and see how they change from G to H. So for example, let's take C on one side and everything else on the other side. In our example, we see that the cut size hasn't changed because the degree of C in G is 3 and the degree of C in H is also G. So this is good for us because it means that the cut size hasn't changed at all between G and H. But since we have removed some edges, some cut sizes aren't going to be exactly preserved, right? So for example, if we take B on one side and everything else on the other side, then we have that the size of this cut in G is 2, and the size of this cut in H is only 1. So that means that this cut isn't exactly preserved. And this might look bad, but what we can say is, hey, the cut size hasn't changed by too much, right? So in this case, the cut size of B on one side and everything else on the other side has only changed by a factor of 1/2. And so what we want to say is, any cut in G only changes by a size of like 1/2, by a factor of 1/2 when we look at its cut size in H. So that's kind of our idea for our sparsified graph that we want to use. So we're going to take this result from a result proved by Anand Guha. And the idea is we're going to, so our sparsifier is going to do this. It's going to construct a graph H, so our sparsified graph H, that fits within our space bound. Remember, because we have to have like only O tilde n edges. And so we say we start with this an example graph G, and then we construct a sparsified graph H. And our guarantee that we said was that each cut size in G changes by a factor of at most 1/2 in H, right? And we're going to say, we're going to generalize this. So instead of some factor of 1/2, we're going to say that there's a factor delta. So each cut size in G is delta approximately preserved in H. So all that means is, say I have some cut in G, then we know that its size in H isn't going to be too different from its size in G. So it's only going to be between 1 minus delta times its size in G to 1 plus delta times its size in G. So all this means is that this cut in G is delta approximately preserved in H. Okay, so what do we have so far? Our argument is basically saying we cannot store the entire graph in the first pass. So we're going to store some sparse-wide graph H. And remember, we wanted in this part, we wanted to get the min cut of the graph. So what we might say is, hey, okay, I'm just going to run some min cut algorithm on H and then get a min cut, say C prime, right? Where C prime is the min cut of H. And then let's see what happens when in this third step, we store the edges across this min cut C prime and then return the partition in size that way. So we're going to store the edges across this min cut of H C prime. Okay, so what is our algorithm going to look like then? So we're going to have our input graph G, and then we're going to get the information of G through a stream, right? And at the end, remember in the first step, at the end of this input stream, we want to be able to construct this sparse-wide graph H. And we said just now that, hey, we're going to run any min cut algorithm in H and get a min cut of H. So in this case, we get ABC on one side and DEF on the other side. And that's our min cut C prime. And remember, that's exactly the min cut that we wanted, right? That's exactly the min cut partition that we wanted in G. ABC on one side and DEF on the other side. So this is good for us. Okay, so now we have
questions.
Yeah.
So one is that the min cut in this graph H is not unique, right?
Yes.
So I don't know whether if I took the min cut as just A on one side and everything else on the other, it has the same size in H.
Exactly.
So you sort of have to approximate it when you map back. And also, you haven't used the notion of weights in any way so far, right?
Yes.
Okay.
So my example isn't going to use weights. And also we're going to talk about what happens when we don't choose this exact min cut, but we're going to do that in a bit. Does that sound good?
Yeah. Thanks.
Sorry, I just have a quick question. So I forgot the eventual goal. Is the eventual goal to find the min cut or to find an approximate min cut?
The global min cut.
The global min cut. Okay. Okay. Thanks. Okay.
Okay, sounds good. Okay, so yes, so the min cut that we got from our from running a min cut algorithm on H is going to be ABC on one side and DEF on the other side, and that's exactly the min cut that we wanted, right? So in the third step, what we said that we're going to do is when we get the stream, we're going to store only those edges that cross this min cut. So in this case, that's exactly what we do, right? So we only store the edge CD because that's the only edge that crosses the cut. And in the end, we have the correct partition and we have the correct size, and we're all good. But just as Dr. Kuller said, this isn't the only min cut of H, right? So in this case, we chose ABC on one side and DEF on the other side, but there are many other min cuts of size 1 in H. So what happens when we don't choose this particular min cut in the second step? Okay, so we're going to start with our input graph G and get it through a stream and construct some sparse-wide graph H. So far, everything is the same in this iteration of the algorithm. However, in step 2, when we run some min cut algorithm on H, we choose the min cut A on one side and everything else on the other side. Because remember, this is also a min cut of H, right? Because it has size 1. So now what we're going to do, we have the partition that we wanted, right? So from this step, we got the partition, and then we throw H away. We don't need it anymore, and we're only going to store the edges in our second pass we're only going to store those edges that cross this min cut, right? So when we get the input again, we now are storing 2 edges, right? One from A to B and one from A to C. And realize that this is not what we wanted, right? This is not a min cut of the graph, and we've returned the wrong thing. Okay, so where have we gone wrong? We went wrong in this step, right? When we said that the min cut of our graph G was A on one side and everything else on the other side. And that's bad, right? That's a case that we don't want to do, because after this step, we just completely lost the min cut of G. And we don't want to do that. So how can we remedy this? So remember, we're taking the case in which the min cut of H is not equal to the min cut of min cut of G, and we don't want to lose our min cut G. So what is the bad case that we're getting tripped up on? So here we have a diagram of the cuts in G. So we have like a stack of cuts in Z and a stack of cuts in H, where the lowest member of the stack is the min cut, right? So C star, and then the lowest cut here is C prime, so the min cut of H. And the cuts increase as you go up the stack. Okay, so when will C star, when will the partition C star not be the min cut of H, right? So the case that we just saw, right, was when some non-min cut shrunk. The size of some non-min cut shrunk in H, and that means that this non-min cut is just going to pose like as a doppelganger min cut, and that causes us to lose our min cut C star. So that's one bad case. And then another bad case is when this our min cut C star actually increases in our sparsified graph to C star times 1 plus delta, and this is bad because now it looks less like a min cut of H. But we can say that, hey, C star,
so C star can't go up if you're just sparsifying the graph, right? If you're only sparsifying the graph, how does C star go up in size?
Right. So this might happen because we're now putting weights on the edges. So that's how if we increase the weight of an edge, then our min cut might increase. Okay. So yeah. So but we can say though that our cut C star isn't going to go too high in the graph, right? Because remember, this sparsifier is only going to approximate by at most delta factor. So we can say, okay, we can take some range of cuts C from the bottom of the stack H. And so say, in this case, we have this red range of cuts where C star is guaranteed to be within. So we start from the bottom, take some red range of cuts, and say, hey, C prime must lie somewhere within here. Okay, so how are we going to get this set C hat? Okay, so we do a bit of algebra, and at the end we get that the range C hat goes from the bottom of the stack, C star, to some approximating factor like 1 plus delta over 1 minus delta. And if we take all cuts in this range, we know that C star must lie somewhere within there. So that is good, because now we haven't necessarily lost our min cut C star. Okay, so what do we have so far? Well, remember in the first step we said that we're going to get our sparsified graph H.
Can we go over how we found the upper bound on that range again? Because we know C prime, we just run the min cut algorithm on the sparsified graph H. But how do I find C star 1 plus delta?
Right. So all we're doing is C hat can only be so much less than C star. And then we say that the max size of C star in H can only be so much more than C star. So then if we combine those two bounds, we get this. It's just a bit of algebra. You can see it like here.
But we don't know C star, right?
We don't know C star. But we know that it can't get mapped too high in our sparsified graph H.
Okay. Yep.
Okay, sounds good. Okay, so so far we have our sparsified graph H, and then we said before that we would only get the min cut of H and then call that our partition. But remember, we're going to lose our we're going to lose C star in this step if we do that. So instead of getting just one min cut, we get some set of approximate min cut C hat. So C hat is just some set of cuts, maybe C1, C2, and C3, but we know that our min cut C star must lie somewhere within there. Okay, so now let's look at our third step. So in the third step, we say we get the input again and store the edges across the min cut, but hey, we don't have only one min cut now, right? We have like multiple min cuts. We have some set of approximate min cuts. So we need to know how exactly we're going to store the edges across all of them. But we know that it can't get mapped too high in our sparsified graph H.
Okay. Yep.
Okay, sounds good. Okay, so so far we have our sparsified graph H, and then we said before that we would only get the min cut of H and then call that our partition. But remember, we're going to lose our we're going to lose C star in this step if we do that. So instead of getting just one min cut, we get some set of approximate min cuts C hat. So C hat is just some set of cuts, maybe C1, C2, and C3, but we know that our min cut C star must lie somewhere within there. Okay, so now let's look at our third step. So in the third step, we say we get the input again and store the edges across the min cut, but hey, we don't have only one min cut now, right? We have like multiple min cuts. We have some set of approximate min cuts. So we need to know how exactly we're going to store the edges across all of them. Okay, so remember before we said that storing the edges across our min cut was just like creating two supernodes and then storing only those edges across the supernodes? We're going to do a similar thing here with many cuts, right? So say in C hat, we not only have this cut C sub 1, but we also have this other cut C sub 2. So we not only have our min cut C1, but we also have C2 in our set C hat. And we need to preserve all the edges across both of these cuts, right? But there's some edges that are useless to us. So these two edges are useless because they don't cross any cut in C hat, right? So we're just going to contract them just like we did before, and we're going to end up with this time a 4 supernode graph. So notice that if we run any min cut algorithm on this, we'll get the same min cut size and partition as our original graph, right? So if we run a min cut algorithm on the supernode graph, we'll get that the min cut is ABC on one side and DEF on the other side with a size of 1. And that's exactly what we wanted.
Is there a bound on how many cuts you want to keep track of?
No, but we will go over that.
Okay.
Okay. But yes, good question. Okay, so yeah, so what do we have so far? Remember, we have our specified graph H, and from that graph, we get our set of approximate min cuts. And then what we just said was we're going to store all of these edges across the approximate min cuts in a supernode graph. Let's call it maybe G sub S, right? So after we store these edges in the supernode graph, then we find the min cut of the supernode graph and then return the partition in size. And this would be a good algorithm, except the space doesn't work. And so we'll see why in this third step, our space might exceed our limit. So one bad example that we could say is if we're trying to preserve all the min cuts of a clique. Remember that all of the min cuts of a clique, so we're trying to store preserve all the approximate min cuts of the clique in our supernode graph, right? But the min cuts of a clique are just all, so if we take one vertex on one side and the rest of the vertices on the other side, that creates a trivial min cut, right? So all min cuts of this clique are trivial min cuts. And that means that we need to store all of the edges of the graph because we need to store all the edges that come out of each vertex. And this is bad because that means we're storing at least n squared edges and our space breaks. But notice that we can solve this a little because all min cuts of a clique are trivial min cuts. And there's something special about trivial min cuts. And the thing is that they're easy to find. What do I mean? I mean that the size of any trivial min cut is just the degree of that vertex that is isolated, right? So to find the degree of any vertex or all vertices, you can just, as you're getting the stream, add 1 to the degree of each vertex that the edge that you're getting is incident upon, right? So in this case, if we get edge AB, we just increase the degree of A and we increase the degree of B. And at the end, we should be able to find the size of all trivial min cuts. And we can just do this in the first pass, right? So the problem of finding the min trivial cut is just, we can just do that immediately in the beginning and be done with it. So what we're going to do then is separate our problem of finding trivial and non-trivial min cuts.
I have a question.
Yes.
What do you mean by a trivial min cut? Is it just one vertex and everything else?
Yes, exactly.
Okay.
Okay, sounds good. So we're going to separate our problem into finding trivial and then non-trivial, right? So in the first step, just right away, we can store the trivial min cuts in step 1. And then what we can do is, in the rest of the algorithm, only focus on non-trivial min cuts. And then at the end, we should be able to compare the trivial min cut that we found in the beginning with the non-trivial min cut that we found later on, and then output the min of the two. Okay, so how is this going to look? So this is our algorithm. It might look like it changed a lot. It really hasn't. All we did is add our storing of trivial cuts to our first step, right, as we're getting the input, so that we can just find the min degree and be done with it, right? We can be done with our finding of trivial min cuts. And then we're only going to focus on non-trivial min cuts for the rest of the algorithm. So in C hat, we're only going to include approximate non-trivial min cuts. And that means that in our supernode graph, we're not going to store trivial min cuts anymore, right? We're only going to store the edges across non-trivial min cuts that we have in C hat. And then at the end, we get the non-trivial min cut from our supernode graph G sub S, and then compare that with the min degree, and then which is the trivial min cut. So we compare the non-trivial and the trivial min cuts and output the smaller of the two. And we're at the end of the algorithm, so we're good.
Hey, can I just interrupt you for a second? So
Yes.
can you repeat what the issue was with these trivial min cuts? I guess the reason I'm asking this is because wouldn't a similar issue occur when you have min cuts with two vertices on one side and n-2 on the other side, or other very small cuts, unbalanced cuts? So
Right,
what was the real issue with trivial min cuts again?
So our issue was that we had like bad storage when we included trivial min cuts, right? And it turns out that if you just take away those trivial min cuts, so if you just treat those trivial min cuts separately, your space actually becomes like much better. So you can just store these trivial min cuts on their own, and then your space magically becomes good.
I see. So this is in the sense of storing it using these supernodes. Like,
Yes.
Okay. So you're looking at the supernode graph where you can actually effectively store all of these min cuts, all of these small cuts. I see. And for a clique, okay, thanks. Okay, right.
Awesome.
Okay. Yeah,
Okay.
just to make sure I got it right, the point is that if you have to store all trivial min cuts, you'll have to have all of the nodes as separate nodes, and you won't have any contraction with respect to the supernodes.
Exactly.
Okay, thanks.
Awesome. Yes, exactly. Okay. So yeah, so this is the algorithm that we're going to use. So now what we're going to do is see, okay, now that we have separated these trivial min cuts, does our storage work? And it turns out yes, so our storage does work now. And what we can show is that if we have some set of small non-trivial min cuts, then they will have at most O of n edges together. And what that means is we want to say, hey, all of the cuts in C hat are small, because if we say that all the cuts in C hat are small, then after we show this, then we'll be all good. And you might be thinking, hey, we already showed that all of the cuts in C hat must be small because we said that they're only like some factor away from the bottom of the stack, right? But this is the stack of H, right? Not the stack of D. And remember, in the supernode graph, we're storing the edges in G, right? We've thrown H away by that time. So what we need to say is, hey, this red range of cuts will correspond to some green range of cuts such that anything outside this green range of approximate min cuts cannot get into this red range of cuts. So all that means is we can say that all cuts in C hat are epsilon approximate in G. So if we take some cut in C hat, then its size in G is at most like 1 plus epsilon times the min cut of G, so C star. That's all we're saying. Okay, so we've gone over like the algorithm, and now we'll work on proving it, right? So this is just our algorithm from before, and we're just going to go over what we need to prove for each step. So first off, we say that we're going to store the information in Spartifier. We're not going to go over how exactly that works, but yeah, it was proved by Anguha earlier. So then we're going to focus on is this next step, where we say that we're going to store the degrees of each vertex. Because remember, that's how we're getting the trivial min cuts. So we need to say, okay, so does that fit within our storage space? So let's just quickly go over that. We have n vertices, and we need to store the degrees of each vertex. The degree can be between like 0 and n minus 1, and that means that that number is like less than n, so that means log n space for to store that degree. So we have n vertices and log n space for each, n vertices and log n space for each, so in total we have like n log n space, and that fits within our bound. Okay, so our first step is done. And in the second step, we said that we're going to get some set C hat of epsilon approximate min cuts, right?
Hold on, so the log n actually just came from the bit representation of the nodes, nothing else.
Yeah, exactly.
And there's no, so it's not even polylog, it's just n log n space? Or there'll be another log n factor coming in soon?
I mean,
so when you're
I don't
counting
think
space, you're just counting bits. Okay,
Yeah, I counted that in bits.
I see. Because many people assume that you can kind of store a vertex label in a word and then they count words, but that's
Right,
not
but
what
the
you
log n space was for the number of edges, right? So it wasn't for the for like the label. It was just for the number of edges that we're storing.
Okay. Thanks.
Okay. Okay, so yeah, so in the second step, we said that we're going to get some set C hat of approximate min cuts. And we just said, like right before this, that we need to show that the cuts in C hat are epsilon approximate. And we're not going to go over that right now. It's just a bit of algebra, but you can show that all cuts in C hat have an upper bound on their size in G. And then what we're going to do is, using these approximate min cuts, we're going to make a supernode graph, right? That's what we said that we're going to do. And then first off, we need to show that we are good with we can store the information of the supernode. So what do I mean? I mean that each vertex needs to know which supernode it belongs to, right? So we need to know that that storage space is within our bound. Okay, so this is exactly like the degree storing degrees. So we have n vertices. Each vertex needs a supernode, and that can go from 1 to n. So that's like log n space for each vertex. So n log n space in total, and we're all good. Okay, so now we know that storing the information about the supernodes is all good. And now what we can focus on then is like the big part, right? We need to know that the number of edges that we're storing in the supernode graph isn't too large. And we said before that we can show that the storage space is only O of n edges. Okay. So our goal is to store, as we just said, store all of the edges across all cuts in C hat. So it might look something like this, right? We have some cuts in C hat, C1, C2, and C3, and we're just storing all of these blue edges that go across them. And the guarantees that we have are that all of these cuts are non-trivial, remember, and also that the size isn't too large. The size of each cut isn't too large. So we're just going to say that all sizes are less than C star plus epsilon D, where D is the min degree of the graph. Okay, so we're storing these edges across approximate min cuts, and we want to know when do we have less edges to store, because that's our goal, right? We want to show that we have less edges to store. So we say, okay, maybe if we have a small number of cuts to store, then we'll be all good. Because if we have a small number of cuts and then a small number of edges per cut, because these are min cuts, then in total we'll have just a small number of edges if we pay for each of them separately, and we're all good. Okay, but it could be that there aren't a small number of cuts in C hat. So instead of this graph G only having 3 cuts, so 3 lines across it, we might have like many edges across it, many cuts across it. And this is bad because now we cannot pay for all of these cuts separately. That would just be way too many edges.
And in some sense, this is the same issue that you were running into with the clique and the trivial case, right? To some degree.
Yes.
Because each node was creating its own cut, so you had an order n cuts.
Right. So if these tiny cuts get too small, then we'll have it. If these tiny like partitions get too small, then we'll have an issue. Yeah. Okay. Awesome. So so if we have many cuts, we run into an issue. But then we realize, hey, maybe we don't need to pay for all of these cuts separately. Because before we said that with the small number of cuts, we're going to pay separately. Maybe in this case, we don't need to pay separately. So say we decide to pay for some blue cut here. And then we look at some red cut, which we want to decide if we should pay for it or not. And we realize that no, we probably don't want to pay for it, right? Because most of the cuts that cross this red cut are also going to cross the blue cut. So it would be such a waste to just pay for both for those edges twice. So what we're going to do is we're going to think like this and say, okay, we're going to choose some set of like representative cuts, right? So some blue set of representative cuts. And we're going to pay for all the edges across these cuts separately. So we want to choose some small set of representative cuts and then pay for them separately. So that's one thing that we want to do. So this kind of ensures that we don't pay for edges too many times. Okay, so now what we need to make sure is all of the green cuts that we haven't counted in this set of representative cuts, we need to make sure that these cuts edges are like accounted for, right? So let's look at some edges that might cross this green cut. So we could have this edge that crosses the green cut, but we can see that this edge has already been counted, right? And when we paid for these representative cuts, because like this blue cut has this red cut across it already, so we would have already paid for it. So that's all good. But there are some edges that will not be across any blue cut, right? That will be across this green cut, but will not be across any blue cut. So for example, this edge. And what we're going to say is, okay, there cannot be too many. Okay, so each edge that we haven't paid for must have one vertex that's like in between the cuts, right? Like there aren't too many vertices between these two cuts because they're very similar. And all edges that we haven't counted must have like one vertex like in between these cuts. And we're going to say that, okay, if we say that all the edges coming out of these in-between vertices, if we count all edges that come out of all in-between vertices, and we say that that amount is small, then we know that the rest of the edges that we haven't counted yet, that amount is also small, because all the edges that we haven't counted yet must come out of some in-between vertex. So essentially what we're doing is we're paying for the rest of the edges that we haven't counted yet in bulk, and we're doing that through these in-between vertices. So what have we said so far? We've said that we can take some set of representative cuts and pay for each of them separately. And then all the edges that we haven't counted yet, we can pay for in bulk.
Hey,
So first let's, sorry.
Could you, no, no, by the way, this has been very clear so far. So I understood, at least I think I understand most of what you said so far, except that these blue cuts, so these have to be disjoint, is it? Or are they just a bunch of representative cuts? So why do they have to be, I mean,
okay.
I of them as disjoint in the set of edges that cross? Yeah, so what do you mean by disjoint cuts again?
So, okay, so say we took some representative cut that was like very close to some other representative cut, right? Okay. We might as well not include this purple cut in our representative set because a lot of its edges are going to cross some other blue cut anyway, right? So we might as well just not pay for it separately. Like, does that make sense? We'll go into what exactly we mean by disjoint cuts or representative cuts.
Thank you.
Okay, awesome. So yeah, so we'll go over how we're going to count all of these edges across disjoint cuts. And remember, we're paying for them separately. Okay, so this is our diagram from before. And what we're going to do is construct some set of blue cuts. So some set K of disjoint cuts from C hat. So we're going to take all cuts that we want to pay for. So all cuts in C hat, and we're going to choose some set that some set of disjoint cuts from our entire set. Okay, so, and remember, we want the partitions between these cuts to be kind of different, because remember, if we have many cuts, right, or if we have cuts that are very similar in like their partitions, if we have a lot of cuts with very similar partitions, they're going to have a lot of edges that overlap. And this is bad because we don't want to pay for those edges multiple times, right? So we want the partitions to be different. Okay, so we're going to start building our set K. So we're going to start with K is empty, and then we're going to iterate over all cuts in C hat and decide which ones get to be disjoint and which ones aren't so disjoint. So we're going to do this by maintaining a supernode graph. So remember how we use supernode graphs in our algorithm? It's going to be like basically the exact same thing, except instead of making a supernode graph of cuts in C hat, we're going to make a supernode graph of cuts in K. So in this case, when K is empty, our supernode graph is just like one big supernode because there aren't any cuts in K. Okay, and then what we're going to do is, as we keep adding cuts to K, or as we test each cut in K, we're going to see if it splits any previous node into two quote-unquote large nodes. And this large thing is kind of how we're making the partitions different. So what exactly do I mean? I mean that, say we were trying to add some cut C sub 1 into K. And it will split our previous supernode, right, the supernode of all vertices, into two supernodes. And we want to see, okay, are both of these supernodes large? If they are, then we'll add the cut to K. What exactly do I mean by large? So what I mean is, if the size, so if the number of vertices in the supernode is greater than some amount, we're going to call it large. And what amount is that? So we're going to choose some constant beta. So we get to choose beta. And D is the min degree of the graph. So we're going to say that if both of these supernodes are of size greater than beta D, then we'll add the new cut to K. So that's kind of the way that we're going to choose this set of disjoint cuts. So let's go through a couple of examples. So say we're at a point in our construction of K where we have 2 cuts in K. So we have C1 and C2, and then we're going to add other cuts to K and see how, see if they belong or not. So let's first try this cut C sub 3. So let's see how it splits the previous supernodes into new supernodes. And we see that since all of these new supernodes are of size less than beta D, we're not going to add C3 to the graph, C3 to our set of disjoint cuts because it doesn't fit this criteria. Now what we're going to say is, okay, what if instead of all of them being less than beta D, actually 2 of them were of size greater than beta D? But remember, so what we're going to do is we're going to ask each previous supernode, hey, were you split into 2 supernodes of size greater than beta D? And both of these previous supernodes are going to say no, right? Because that criteria was not met. So in the end, we're going to not add our cut C3 to the graph. Okay, so C3 is gone. Now let's move on to some cut C4.
So C3 was the blue line that you showed, right?
Yes. C3 was.
Okay.
Okay. So yeah, so now we will try and add some cut C sub 4, right? So we see how C sub 4 splits the supernodes, and then we ask each previous supernode, were you split into 2 supernodes of size greater than beta D? And this supernode will say, yes, I was. And that's all we want, right? Even if the supernode says no, we're fine with that, because all we need is if any previous supernode says yes, then we'll add the cut to K. So we add C4 to K and we're good. So that was kind of the example that we went through. And so far we have said what exactly it means to be a disjoint cut.
Hold on, back up. So did you assume that when the algorithm starts, you know?
Wait, sorry, say that once more. It lagged out in the end.
When the algorithm started, did you assume that you know the min degree in advance? I know you can compute it easily, but that would be another pass, right?
So yes, but this is all. So everything that was said, like with the storage here, it's only for analysis. So this has nothing to do with like our algorithm.
Oh, I see.
Right.
Okay. I'm missing one insight. So anyway, we'll come back and talk later.
Okay. Yeah. So all of that we've talked about was like disjoint cuts and paying for them separately and the rest of them in bulk. That's just proving that our storage space in the supernode graph that we're doing in step 3, we're just proving that that is like O of n edges only. So this is just kind of a bubble of provingness. Okay. So yeah. So what we've said so far is we've defined a set of disjoint cuts K. And our goal now is to say that, hey, if we're paying for these disjoint cuts separately, there cannot be too many cuts in K. Okay, so we're going to say that the size of K isn't too much. So for simplicity's sake, we're going to call K, like small k, the size of our big set K. So what we're going to say is if this size is small, then we can pay for all of the cuts in the set of disjoint cuts separately, right? So what does it mean to pay for each cut separately? So we're going to pay at most C star plus epsilon D for each cut times K cuts. So in total, you're only going to pay for at most like 2 KD edges. And then what we want is that this cannot be more than O of n, right? So what we're going to say is, okay, after a bit of algebra, we can just say that K needs to be less than O of n over D. And if this is true, if we can prove that, then we can just definitely pay for each cut in K separately, and our storage space will be at most O of n. Okay, so how exactly we're going to do this? Well, first we're going to say that a big supernode is one that is of size greater than beta D, right? And then what we're going to do is build K up and say that, okay, every time you add a cut to K, you must also guarantee more big supernodes, right? And if you have too many big supernodes, then at some point you're going to exceed n, right? And exceed n vertices in total in the graph, and that cannot happen, right? So since every time you're adding cut, you add a big supernode, then you cannot add too many big cuts because you cannot add too many supernodes because there are at most n edges. So that's kind of the idea. So first, in the beginning, we start with k is empty, right? And when k is empty, the number of big supernodes is 1. That's just a supernode of all vertices, right? And we're saying that each time you add a cut, the number of big supernodes increases by 1. So let's take a case in which we have 2 cuts in k. So we take the at some point we'll have 2 cuts in k, and there will be maybe 3 big supernodes in our graph. And let's see what happens when we add a cut, right? So we're adding a cut to k. So say C sub 3. What C sub 3 will do, it'll break a previous supernode and it'll make 2 new big supernodes out of it, right? That was our criteria for adding C sub 3 in the first place. So what we've done is from our tally of big supernodes from before, we subtracted the 1 because we broke a supernode, but then we add 2 because we are guaranteeing 2 new big supernodes. And so in total, our size of big supernodes has increased by 1. So this is exactly what we wanted, right? So we've said that at the beginning, we started with 1 big supernode, and every time you add a cut to k, you add a new big supernode. So after adding k cuts, then you must also have k more big supernodes. So in the end, you have k plus 1 big supernodes. And so now all we need to say, sorry?
Isn't it the case that like the number of supernode can stay the same? Suppose you cut through 2 big supernode, right? And for one node, you get 2 more big supernode, but for another node, it gets split into 2 like smaller supernodes. Then the number of total supernode will stay the same.
Sorry, can you say that once more?
Okay. Suppose you cut through 2 big supernodes, say like B1 and B2.
Yeah.
And B1 gets split into like 2 more supernodes. So
right.
That means that you like this is a good cut, right? But for B2, it gets split into 2 small supernodes. Right. Then that the number of big supernode in your graph will stay the same.
Right, exactly. But the thing is, we're only going to split the supernodes that C3 guarantees, what we're going to, so we're only going to split the supernodes that are good for C3, right? We're not, if this previous supernode was bad for the new cut, then we're not going to split it up, right? We're only going to split up the supernodes that are good. Does that make sense?
Yeah. Thank you.
Okay. Awesome. So that was a good question, right? Okay, so awesome. So we have k plus 1 big supernodes. And now what we're going to say is, okay, we have k plus 1 big supernodes, right? And beta d vertices per big supernode, at least. And in total, since they're all disjoint, they must have less than n vertices in total. And after a bit of algebra, we can say that, okay, k must be at most O of n over d, which is exactly the bound that we wanted, right? So now we can say definitely that after counting all of the edges in all disjoint cuts k, we will end up with only O of n edges. So we have paid for all these cuts separately, and we're all good. So now what we need to focus on is paying for the rest of the edges in bulk. Okay, so when we talk about the rest of the edges, what edges have we not counted yet, right? So if we take this diagram, the black cuts are the cuts in k. So far we've counted the edges across those cuts in k, right? So all of these green edges across these black cuts. But what we haven't counted are the cut edges that lie within some supernode, right? So these red edges are cut edges that we haven't counted yet, and this is bad. So let's take some red edge and zoom in on it, and zoom in on its supernode as well. And what we're going to do is there must be some min cut that for which this edge contributes to, right? So let's just break the supernode with that cut. So that blue cut. And it turns out that we must have that one of the edges must live within a new supernode of size less than beta d. And this is because if both supernodes were of size greater than beta d, then this is bad, because I mean, that's a contradiction, because we would have added this blue supernode already to our set of disjoint cuts k. So we know that one of them must lie within a supernode of size less than beta d. And what we can say is that you cannot have many neighbors inside this new supernode, because there are only like beta D vertices in that supernode, so you can't have that many neighbors. And therefore, we're going to say that this vertex is squished within this small supernode. Okay, so note though that if you are in a min cut, you must have more neighbors on your side of the min cut. Because say you don't have more neighbors on your side of the min cut, right? That means that if you just go to the other side, you're going to decrease the size of this cut, right? And that's a contradiction, because if you decrease the size of a min cut, that must have not been a min cut in the first place. So we're going to use this idea. So what we're going to say is, if you're any vertex and you have a min cut, right? If you draw a min cut and you're any vertex in the graph, you cannot have more than half your edges across the cut. And also, if you're a squish supernode, not only can you not have more than half your edges across the cut, but you can also not have more than beta edges within your small supernode, right? So where are the rest of your edges going? The rest of your edges must go outside your supernode. So you have like half here, beta there, and then like 1/2 minus beta outside your supernode. So let's see how this looks in our previous diagram. So here we have that you can have only at most half black edges, and then at most beta blue edges. So the rest of your edges going outside the supernode must be at least half minus beta. And notice that this is like kind of approximate, because these are not exact min cuts. There's approximate min cuts. But what we can say is we can prove that at least some fraction of your edges, if you're a squish supernode, must go outside of your supernode. So we're going to call this fraction alpha. And we're going to say we can prove that at least half alpha of your edges must go across, must go outside of your big supernode. Okay, and we can calculate this, but it's just a bunch of algebra, and it's kind of similar to our argument from before. So we won't go over that today. Okay, so we have a guarantee on the number of edges coming out of squish vertices. And we want to know, how is that useful? Because remember, we want to count the total number of edges coming out of squish vertices, because that is an upper bound on the number of edges that we haven't counted yet, right? The number of edges that we need to pay for in bulk. So we need to know how alpha helps us do that. And it turns out that it helps us because now we know that each squish vertex has already contributed alpha of its edges to the disjoint cuts that we counted before. And we know that there are only O of n edges across these disjoint cuts, right? Because we just counted that. We know that there are only O of n edges across the supernodes. So if we count the total number of contributions of each squish vertex, we know it cannot be too large. And in specific, every edge that goes across the disjoint cuts can be contributed to by a squish vertex at most twice, right? So if this left vertex is a squish vertex, then we would count it once. And then if this right vertex is a squish vertex, we would also we'd also contribute to that edge once. So in total, you can only contribute to this edge twice, and that's it. So if you count the total number of contributions of squish vertices to the edges of disjoint cuts, then that'll be like at least alpha degree V contributions per vertex. And in total, that can be at most 2 times the total number of edges across all disjoint cuts, which is also just O of n. And then what we can do is we can take alpha outside and then divide by alpha on both sides. So what we're saying is that instead of just having a bound on the total number of contributions of all squish vertices, we now have a bound on the total number of edges coming out of squish vertices. And we know that since alpha is just a constant, this will also be O of n. So what we've done is we've counted the total number of edges coming out of squish vertices. And every edge that we haven't counted yet must have at least one vertex that is squished. So this O of n counts all of the edges that we haven't counted yet. So what we've done is we've counted for all of these separately, and we've counted for the rest in bulk. And in total, we have at most O of n in each, so O of n total. So let's just quickly go over what we've done to prove the storage of the third step. So first we said that we're going to take some set of representative cuts and pay for each of them separately. And we want to make sure that the size of this set of representative cuts is small, so that once we prove that there are a small number of cuts that we're paying for separately, we know that there are only O of n edges that we're paying for in this step. And in the second step, we said, okay, we need to pay for the rest of the edges. And these edges we're going to pay for in bulk. And we did that through squish vertices, right? Those in-between vertices that we talked about before. And we said that, okay, the total number of edges coming out of these squish vertices cannot be too large. And that is also O of n. So in total, we had O of n edges. And we're done with the storage for the third step. And finally, what we want to show is that at the end, we output the right answer. And we're not going to go over exactly today, but basically all you have to say is that, so the basic idea is you get the a min trivial cut from here, and from the supernode graph, you'll get the min non-trivial cut, and at the end, if we compare the two, you will get the right answer. So that's the idea for that. Okay, so let's just summarize what we've done today. So we went over a min-cut algorithm in the streaming model, which takes 2 passes in O to the n space to get the exact min-cut of the graph. And how did we do this? Well, we did this by separating trivial and non-trivial min-cuts. So in the first step, we in the first pass we found the min degree, and that's all we had to do for the trivial cuts. And then from the sparsifier that we also constructed, we found some set of approximate non-trivial cuts, got a supernode graph from that, and we just proved that the total space of the supernode graph is only O of n edges. So after getting the supernode graph, we just find the non-trivial cut from that and output the min of the trivial and non-trivial cuts that we found. I want to thank Professor Sadi, Vihan, and Dr. Gandhi for helping me a lot with this presentation, and I also want to thank all of you for listening to me.
Thank you so much. No, that was fantastic. I missed some little details about the squish nose right at the end. I guess a lot of that got squished into the last few minutes. But no, it was really very clear explanation. So if I just back up, so in terms of the actual algorithm, right, is there a succinct pseudocode description? If you didn't have to worry about the proof, like I'm just trying to think as you process each edge, EI, the next edge in the stream, like what is the exact computation that happens? That's what I was trying to mentally see. Like if I didn't care about a streaming model, like does this give rise to a competitive global min-cut algorithm in terms of running time?
Okay, so the only issue I think is the sparsifier in the first step. So as far as I know, the way that you, so I'm not entirely sure about this, but the way that you get the sparsifier is you just try all possibilities at each step. I'm not entirely sure if there's like been a improvement on this, but this is what I was told. So,
I see.
Yeah, so I'm not entirely sure if that's something that you would want to run, like practically.
Yeah.
Actually, yeah. On a related note, I guess I was wondering. So this algorithm is a streaming algorithm which uses no memory, but then is there a guarantee on the running time? Because there is like these approximate non-trivial min cuts that you need to list, right? And you may need to go over. Is that something that can also be done efficiently? By efficiently, I meant in terms of running time, or do they just say you can just run over it exhaustively? And
yeah, I'm not entirely sure how we're getting, like how you would get the set of approximate non-trivial cuts without like finding the size of all cuts, but like
no, it's just fine for the streaming setting because you only care about memory. But
exactly, yeah.
Okay, I see. Okay.
Cool, thank you. So I know you have a bunch of meetings. I've not actually run to another 3 p.m. meeting, but I think you're in pretty good hands. And then you can just stay on this call, and the people who are going to meet with you in the next couple of hours will just join this meeting room.
Okay, sounds good.
And thank you so much again. And then the rest of the crowd can take off to let you chat with them one-on-one.
Yeah.
Okay.
By the way, I just wanted to say that I really enjoyed the talk too, and I learned a lot from the talk. Thanks a lot. Yeah.